So there are many other applications, like interesting, like pseudo-random properties of expanded, right? We call it pseudo-random because it looks like a random in the click. So there are many others, and in the course about spectral graph or expanders, you see like 4 or 5 of those. We'll just do one here, and you will do one normal. It's on the mixing level, very important. Difficult. But let's go on and ask, how small can omega be? I mean, you want expanders that are good, but omega is small. Omega, the maximum omega 2 and omega is small. How small can we make it? And of course, we can make it 0. If you take the click, it's 0. The question is, for an irregular graph, 60. Otherwise, and well, you know that the eigenvalues you can change. So they can't. And so think of omega 2, 4 omega 2. He has one eigenvalue before him, the D1 in this case, right? And all the rest are from the other side. So they're kind of pushing towards the all ones, but they're the one eigenvalue 1. So because of this repulsion, if you know about these things, you can kind of expect what should happen, but we will do it differently. So I'm going to tell you kind of the answer and sketch the proof. Okay, it's not really important for us to be sure, but I wanted to see it. So it turns out, so there's a theorem, it's called the Alon-Boppana. But you can see it in a paper by Neely, which was a baby at the time the paper was written. We found out it's a water. Could be. Probably help a little bit. So what it says is that omega. So let me just. Here it's actually more convenient to talk about lambda. Omega is at least. So I want to say that. I want to say that omega is at least, you should really think about the numerator because this is just an normalization. So omega is at least twice the square root of t minus 1. You want it to be small. Right, I want it to be small, so that's like a limitation. But actually, it's not really true. So what you can say many things. For example, you can just give it the exact number. That's a good number. The exact number is a good number. So what do you see? So you should think of this as the quantity that you cannot go below. It's not quite true. You can go a little bit below it. Asymptotically, you don't see it, but just finite small graphs you can see. So I don't want to be wrong. See, this is a 1, okay, and that's something that's going to go 0 as the number of vertices in the graph goes to infinity. So in this case, the diameter of the graph. So, the click, for example, has the diameter 1 or whatever. But if you have a d-regular graph on n vertices and it's fixed, then the diameter is at least like log n, basically. So that quantity goes to infinity for d, which is fixed, and when n goes to infinity. That's what we care usually about. Want maybe d which is fixed and then goes to infinity, or maybe d which goes to infinity much lower range than n. But this definitely goes to infinity. So you don't really see that, and you should only think of this. So that's the actual one. Yes. So let me show you why this is true. But I'm lying, and my lie is this one. Because it's kind of we don't need it. I don't even this one. I don't know. I won't feel comfortable seeing it. So okay, you want to understand omega. And the problem is that the eigenvalues are like, how can you isolate omega? Right? How can you do that? So the first thing to know is that the trace of the. Do you mind if we work with the unnormalized version? So A is the adjacent symmetric, it's easier for me. Okay, so that's the eigenvalue omega time. We want to bound omega times z. But the trace of A, what is it in terms of the eigenvalues, which are the lambda 1 and lambda d? Right. And the first one is d, and the other ones are, in absolute value smaller than the lambda 2. Okay, so I didn't hold anything very different. This is the unnormalized version. It's easier here because we are going to do some combinatorics.
Is it supposed to be like the I instead of 2?
Yeah. Yeah. Although in the boundary, yeah, okay, yes. And I want to figure out lambda 2 or lambda n, the largest one, absolute value here. So how can I do that? I mean, instead of looking at the trace of A, I'm going to kind of look at the trace of a large enough. I'm going to take an even number, so the absolute value won't matter. And then that, right, it's the same thing, right? Because the eigenvalues of A to the 2k are the 2k power of the eigenvalues of A. It's still the sum of the eigenvalues, but now this way. So that's good. You see, now what's happening is that if k is very large, right, so this is at most d times 2 to the k times. Okay, so the maximum between lambda 2 and lambda n, I don't know which is the largest one absolute value, but that's exactly what I want to understand. I want to understand the maximum, not any of them particularly. So I mean plus times n, or n minus 1 even. Right, so once I did that, you see a large eigenvalue will kind of dominate the sum. Right? Like taking a high norm. So that's a good idea if you want to give a sum and you want to understand the largest element in the sum, you should just take a large power. This is 2 to the k, and the bound is n times. And you see it's already like in the good direction. This would mean that this is lower bounded by something. You understand, but this is the right direction. So that's called the trace method trick. Trace. Yeah, we can actually do this. Right, but it won't matter asymptotically. Affect 0 it will be. And I mean, I'm going to do even something worse than what you pointed out, like I should fix. I'm going to, you should trust me. And again, this is a sketch that I'm going to take k sufficiently small when there is an n here, right? This is small. When k is small, this quantity is much smaller than n. This is like 3 million. So I'm going to take k which is not too large. So this n times that is going to be much larger than. So let me just say that this is roughly the same as, because I'm going to, I promise to choose k which is not too small, not too large. Right, log n to the base d, the diameter or something, but it doesn't anymore. Just we are in the kind of hand waving thing, so I can ignore this. It is not too large, I can ignore this thing. Let's call this thing lambda, because that's a good name for it. Omega for the omegas and lambda for the lambdas. So that's roughly lambda times n. And the error terms are exactly what we count here if you do the actual analysis. It doesn't.
Lambda is the max, the power of 2k?
No, sorry. Lambda is just that. Okay, good. So, assuming that's fine. I just want to bound from below this expression. Trace. But what is the trace of our omega?
It's the number of
Right. Number of cycles. Trace of A. Well, that's right. Trace of A, if you have set loops, they will appear in the diagonal. and you count number of like one length loops. The ratio of A squared is really just the number of edges. Think about it because that's what it is when you do it, but when you go back and forth, it's length 2 walks. And in general, this is just exactly the number of length 2k cycles. Like you start in general, you know. Positive, right? So we need to bound from below the number of cycles. And I don't understand the graph. By the way, here's why the diameter comes, because after the diameter, I do understand the graph. I don't understand the graph. So what will I do? I'm going to lower bound this number by looking at a graph that has no cycles, which is a degree. So I'm going to eliminate the cycles from G. I'm just going to get less cycles now. And I'm going to count how many cycles you have there, and that's a lower bound. Should be formal, but essentially what you're doing, instead of looking at G, you're looking at the D infinite regular tree. No, not the infinite, just some fancy, but you take a DRE tree. So say maybe these 4, it looks like that. Like in such a graph, you have no cycles. But it's not that you have no cycles like built in the graph, but it's not like there are no cycles in the graph in the sense that, I mean, it doesn't have to be a simple cycle. You can go back and forth and that counts as a cycle, right? But there are no like real cycles. If you want to cycle back, you need to go back. Yes. You can take it as with like enough vertices, so that will be we kind of still have a low bound, so a low bound of the number of cycles here will be a low graph on G, but just take it to be infinite.
Okay. Can the final graph is irregular, not a cycle?
Yes.
Without
it may have cycles. It has cycles, and but I want to count, how many cycles do I have, and I don't want to consider the cycle structure of G, which is weird because like that. That's what the number should come from. But actually, there are enough cycles in G coming from the non-simple cycles, silly cycles. Just go back and forth. It's going to give you the bound, and the bound is tight. So the only non-tight part is what I'm hiding. This part, which actually is the crucial part, is tight. It's not obvious at all. So what? So what I'm saying is that I'm going to bound this from below by. So really the number of cycles that don't use the cycles in G. So one way to say it is that I'm going to kind of fix a vertex in the infinite linear graph, but I have n of those here. They have infinity. So here I have n of those. And I'm looking at how many cycles of length 2k are from V, some fixed V. Right, because the trace is just the sum of the diagonal, and every diagonal element is a vertex. So really, I'm asking how many cycles started in a given vertex, and adding up over all vertices. So this n is fine because I'm lower bounding each of the summands, and I'm just adding those. And that n, of course, going to cancel that n. So how many cycles do you have in a length 2k infinite tree?
if you treat every vertex separately,
Yes.
then you have the same cycles.
Right. Here. Like
Yeah.
Yes.
You don't care about that?
No, it's fine. It's only a bound, so I'm lower bounding the number of cycles of each vertex by the same bound. That's fine.
Like in the power of H's, that was taking another of.
Oh, okay, good. That's one part. Good.
You need to down as many times.
Exactly. So you need to multiply these two. So okay, so think about it now. Now asking myself, how many length 2k cycles I have from V to itself in this graph. Let me first of all, let's remove this edge, one edge, it's infinite tree, it doesn't matter. One edge, so that it will be kind of regular, it will look the same all the time. Now it's actually technically not regular, but it looks the same. You see there is I take away this other part of the infinite tree. So every length 2k cycles from V to V, I mean, there are two things you have to kind of, you want to count this. So there are two things you have to specify in order to understand what's the length 2k path. First of all, is kind of, say k is 4. Say k is 4, say k is 6, more interesting. When you have like things that looks like I'm going up and down, and I need to choose a number, a neighbor, but still I'm going up and down, and then maybe up and down, and then maybe up and down, maybe here also. But there are other kind of type of cycles. When I move down twice, go up, and move once down and one up. And it kind of, it reminds you of something like, so right, very good. So you see you have an amazing lecturer that did that. So the number of ways, without choosing a neighbor, just the number of kind of configurations going up and down, regardless of the question of where I'm going down and going down, is this number. You have to choose k times you go down and the rest you go up. Now, when you go down, when you go up, you have no options. But when you go down, you have d minus 1 options. Because I remove that for it to be regular, and then you have d minus 1 options because there's one up and d minus 1 down. So it's d minus 1 to the k. You have k options to go down. You need to specify which neighbor you go down to k times. So this is the kind of the pattern of going up and down without specifying where I'm going down when I'm going down. And for each such pattern, so that's why there is a product, you multiply it by the number of ways you can go down at each step you went down. You see, this is d minus 1. If I wouldn't have removed that, there was a little bit of d here, but it doesn't matter. So slightly more than d times d2, but it's optimal. And this is roughly, if you know your things, this is roughly square root of k times 2 to the 2k times d minus 1 to the k. That's just, I don't really mind, don't care about that. Anyhow, that's something that I don't really mind, times, you see, 2 square root of d minus 1 to the k. 2, yeah. No, 2k. So, okay, so that's where it comes from. The 2 is from the Catalan numbers, and this is from the Arabs. That's really why it appears. I hope it's like less magical now. But anyhow, when you put it back here, so we had lambda to the 2k is at least, and roughly at least, but there is a little bit of roughly there, but at least 1 over square root of k, which doesn't matter, 2 to the d minus 1 to the k, and then 2k. And now if this weren't here, then really we get that lambda is at least 2 to the square root minus 1, but there is something here. So when you will take the k fruits, it won't go away. Like it will go very quickly to 1, but it won't go away. So that's why you need to take k as large as you can, so this won't bother you. But I promise you I'm not taking it too large, so there is a little bit of trade-off here. D, no, here, because there is no n. So that's the n here. So think of this as a small constant. So as long as k is small, d to the k or d to the 2k is smaller than n, regardless of that quantity. I guess you need to make sure it's at least 1 or something. But, regardless of that quantity. It's at least 2 square root of d minus 1, but you need to move it. And so, all right, so a little bit, I cheated a little bit.
You added the lambda to the 2k and you subtracted the
Right, so that's what you should do. You should have d to minus 2k here. That's what it's all again?
No, to go to the quality, you subtracted it to the 2k and you added the lambda.
Only here.
That's good.
Yeah, so I kind of just ignore that completely. And that's fine, because as long as k is not too large, this n factor is much larger than 1. This is not too bad. This doesn't go, that actually is larger than 1. But ignoring that, once I know it's larger than 1, I can ignore that. And then d to the 2k is much smaller than n. Yes, yeah. Here and here.
Okay.
I see. Yeah, so that's how it looks like. because it appears also here. But the trace something that was in minus one there. Because of the trace. So the trace, you got all elements in the diagonal and in the vertices, and for each you ask how many cycles they have, and this is a bound for each of them because they fixed it. So for each vertex in the graph, I'll have at least that many cycles. And there could be more cycles in ignoring them. So the bound sometimes, if you have more information about the graph, you can say, but with under no assumption, this is wrong.
Does it work for any power? If quality graph,
Yes.
the trace of the power like 2 infinity.
Right.
Doesn't go.
No, that's also what they did.
Yeah.
Yes. Well, that's the n. Well, there is the k and the m. K could be much larger than n. It doesn't fit this bound. You can't make it much larger. You would choose k to be roughly the log n, but for this one. But you can still, if you want, you can look at a to the like n, which is like really weird, like way too much steps. Yeah. But you can do that. It still holds, but then everything will kind of break out. Me promising not to take k too large, because then that would be the dominating factor, not that.
We still, you still have that many cycles in the graph? No, because it's an infinite.
Right. Well, no, but you can.
As long as k is like
Right. Right. So there's another bound on k, right? Because of the type of the tree that you got. But most, I guess, log n, because you have n vertices. There are several reasons that k shouldn't be larger than 1. Okay. So I hope this. I mean, this is just a bound. Doesn't mean that there are such graphs. But there are. So let's talk about them a little bit. Actually, it's a very interesting history that happened there. So, what happened was that in the early works of standard, like 40 years ago or something, that's like Middle Ages for us. I existed, but like not really. So there is an amazing theorem by Lubatsky, Philip, and Sarnak, and also my people's students. I don't remember the years exactly, but a long time ago, it appears on the notes, where they actually not just prove the existence, they have an explicit construction of a graph that matches this bound. So there exists an explicit construction. Beautiful, super beautiful. Crazy good. Of irregular graphs. Well, they require D to be like a prime power or prime power plus 1 or something. It didn't work for every D. But for many degrees, there was some requirement there, but for many degrees, once you have this degree, there were of infinitely many sizes. Not sure they had any size. It's for every degree, which is okay, that's a limitation. But other than that, I don't care if they got. I'm fine with having a graph of every power of 2 number of vertices for every application I have in mind. So that's roughly what they get of many sizes that achieve. So the lambda, which is the d times omega, was 2 times square root of d minus 1. Opposed. And so they actually gave an explicit construction, even strongly explicit if you remember the difference. You could look at a vertex and figure out the name of the vertex in time, which is polynomial. Amazingly strong constructions. How they get going? That never happens. Usually what happens is that after 30 years you do it, not in the first year. Fantastic. Fantastic. And a prime. Like the P prime, or probability. So D, what I'm saying is that D couldn't be any number. should have been a prime power. I think it was a prime here and a prime power afterwards. Simulations, but you know that's like amazing. And it's based on the kind of group theoretic and also number theoretic the analysis for that. I mean, for the analysis you need a 1 year course. But if you have the right courses, it's easy. I mean, it's not easy, but it's like a couple of hours. So we won't do that. But I'll just tell you a little bit. So it's still open. I mean, this kind of graph, or maybe I should say that. So it's still open whether a random graph is non. We don't know. Point. When you achieve this bound, you call it a Ramanujan bound. Ramanujan graph. So any graph, every irregular graph with second and last eigenvalues are both 2 square root d minus 1 upon the Ramanujan graph. You know, you can go a little bit below Ramanujan graphs, maybe because of the lower bound, there is some gap. But it vanishes as the number of vertices goes, so we don't care. But that's what we care about, really. We care about large ones. So they actually constructed Ramanujan graphs from groups, and because of that reason, they needed the degree to be something that relates to the group they chose. And the question is whether the first question that's still open, whether a random graph is a Ramanujan. Being a Ramanujan is like a structured thing or a random. So actually, we kind of know the answer because we just ran experiments with people, run experiments, and it turns out that depending on the choice of distribution, depending how you sample a graph, but you know, for any like normal way of sampling graphs, linear graphs, some constant fraction of the graphs are Ramanujan, or slightly below. And this constant depends slightly on the distribution. For example, if you take the perfect matching, then take the union, that's a good way of getting the linear graphs, then you get some distribution, 0.1, whatever. So it's like a semi-random problem. Many graphs have that, but not like 1 minus it.
Remind me again, what is the left side of the inequality?
Lambda?
Yeah.
It's like d times omega. It's like you want this to be at most 2 square root of. Right, and like 10 years ago, there was a sequence of paper by Marcus Gilman and Sevastava that proved the existence of Ramanujan graphs almost, with an asterisk on that, but only existence, right? For any D, which was amazing for many reasons. But the reason like was that it has nothing to do with group theory. It's just we do something else. It's highly non-trivial, even maybe less. I don't know. But, it's kind of based on analytical arguments. You see integrals. But the problem there was that they only bounded lambda 2, like the second largest eigenvalue. So it's a one-sided one. And it's still open to construct a Ramanujan graph of every degree or every size. It's still open to understand what's the probability of a random graph to be Ramanujan. So there are many open questions here. But the big thing was actually established in the beginning, which is amazing. It's really weird. Question about that?
Why are people still trying to do
Good question. So, right, what are we doing, right? So if you have such great expanders, what are you doing inside the expander? What are we going to do now? We're going to do that. Okay, maybe for pedagogical reasons, but for real. So the reason is that, okay, so the constructor Ramanujan graph, very good, amazing. But we sometimes don't just want the graph, we want it to have some extra properties. We want to kind of play with it a little bit. And it's really hard to play with this. They're really rigid. Having said that, there was a big breakthrough 2 years ago that did exactly that. Aside from that, in 40 years, it was very, very hard to play with this thing. So we really wanted like expanders that are more amenable to like adding some updates to the graph, adding some properties. So, and that's the reason where combinatorial construction of expanded came in. So this is a product which we'll talk about in some. Because one, it's something that we can play with. And that indeed proved itself very, very much, because in many applications, for example, in the proof of the SL equals L, which we prove the next time probably, they use not these expanders, but other expanders, because they are easier to work with. So that's why we construct more expanders. We actually have the best expanders we want. You know, model the fact that the degrees, the number, usually don't care about that. And they're also beautiful. I mean, it's not like, you know, it's ugly, how to implement, beautiful, fantastic. It's still the most beautiful construction. Yeah, but that's why. I mean, for practical purposes, really. And the way they constructed that is using groups. So let's do that. Let's do no, not that. Let's so you know in general, you know, this is like a high level talk. Lambda is not you know given a graph. How can you even bound Islam? How can you even understand Islam? It's a weird quantity, right? What? I mean, you can't really look at the graph. I mean, technically, polynomial, you can, but as a human being, you can't look at the graph and say what's Islam. You need structure from the graph to also to you know you need structure under the graph so that you can understand lambda. And groups is the best choice.